In a world where high-performance, zero-defect buildings are hard to find, two men are on a mission to disrupt the status quo. Welcome to the Edifice Complex, the property design and development podcast. Let your hosts Adam Muggleton and Robert Bean keep you up with who is innovating and doing great work, perspective on the adjacent possible, and challenges to the status quo.
Welcome to the Edifice Complex. I'm Robert Bean, your co-host and unofficial mediator, here with my colleague and official agitator, friend, and Yoda of most everything to do with buildings, Mr. Adam Muggleton. Say hello, Yoda.
Hello there. So just so everyone knows, I am the advocate against the status quo. That's it. Things just don't work for me. I'm a ranty old man.
Always good to have you on the call, Adam. All right, and then for today's episode, we're going to continue our exploration of indoor environmental research and buildings, big buildings, with our special guest, Dr. Peter Simmonds, who's an uber practitioner of indoor environmental analysis and systems solutions. Peter, welcome to the show. Good to have you on.
Good afternoon. Thanks for having me.
You're welcome. When did we first meet? 25 years ago, 27 years ago? Something like that. Yeah. Anyways, you gave up a big chunk of your life to get your doctorate degree, and then you ended up in one of the nicest parts of the United States running a worldwide consulting practice. Tell us how the hell you got there.
Well, it was dead simple. As we previously discussed, I wanted to become a footballer, and I was doing really good at that, and I got my way up to Chelsea, and I was playing there. And I didn't quite make it. So other than disappointment and sleepless nights and crying my eyes out, I had the realization of living in England at the time that I couldn't become a beach bum where there was no beach, and I had to get a job. So I applied for two jobs, and one was with BP to work on the oil tankers that go all the way around the world, and the other one was with the Atomic Weapons Research Establishment at Aldermaston to become an apprentice plant fitter. I got the latter one, and I'd done that. So I worked through with the way it worked with school, with part-time college. So I ended up leaving England with two bachelor's degrees, one in mechanical engineering, the other one in research and development. I was interested in motorbikes then and graduated from football and went to motorbikes and went over to the Netherlands to follow the bikes and stayed there, worked for a great company called Raadgeven Technisch Bureau van Hoogten, which was, you could do anything. You just had to prove that it would work and you could do it. Very innovative, great person, Pierre Leyendeckers. There were no rules, no holds barred. We were doing the climate facades. And I guess where we're going to allude to, that's my first introduction with doing radiant systems. We were using radiant ceilings from the old Zent Frenger, which was actually aluminium or aluminum if you're American, which clipped onto steel pipes. And what we were doing then, we were doing actually manual comfort calculations from Fanger. This was 1978, 1979. So we could actually work out how comfortable the spaces would be for the people in the wards. So what they could do is the architects could make bigger windows so the people in the beds could actually see out the windows, and the radiant kept them more comfortable and decrease the energy consumption. A little bit more with another hospital, we had some radiant floors because Netherlands is minus 12 design in the winter. And we had a very simple couple of pipes running down there, which were the heating pipes. Next to them were the cooling pipes. And so we decided, well, let's see what it's going to be like if we run some cool water through the radiant floor and see what happens. And that was literally how the first step with the radiant started. By this time, I'd gone back to school in the Netherlands and got a master's degree in Dutch from HDS Den Bosch, and everything was hunky-dory up to that point.
You said something very important before I let you keep going. You said you made it possible for architects to use bigger windows by using the radiant.
Yeah.
So you're to blame for all of the big glass buildings all over the world. Shame on you.
Yeah, that's it. No. You're misunderstanding the challenge. See, this is one important thing. See, that you cannot design a building by code. Just take an automobile, right, which is one of the biggest things people buy. If you were to design it, if engineers were to design cars, I mean, they'd be like Lego blocks, you know what I mean? They'd have 4 wheels and a bit of a sticker or something like that, you know what I mean? Wouldn't sell. But if you look at how much engineering that goes into the present day automobiles and what goes into a building, the trouble is, where we're going to allude to is that, I'm going to say it now, is America is the cheapest country in the world for construction, in the world. And people look at me and say, what about China? What about Asia? There's no other country in the world where you have value engineered sessions before you finish the design. And it's common. It's completely common. People turn around and we've got this beautiful building. How much is it going to cost? Well, it's going to cost me this much. And we get all these people that are supposed to know anything about money, and they turn around then to the client. They turn around and say, well, we can save you $200,000 from this $350 million project. And the guy turns around and says, oh, that's great. I could have a bit of money left over. Let's go and save $200,000. Or the architect might be pushing and saying, hey, we want better finishes in our toilet so we can upgrade to marble and everything. And what do? They take $200,000 out of the control system for the mechanical system, and lo and behold, it doesn't work, right? And it's very simple. It's the dumbest game on the world, what they do, but they continue to do it, And the fact of the matter is that developers and clients still go ahead with this, and it's a scam. So what then happens is, what they can't see is that you purchase a building for $350 million minus about $3 or $4 million worth of product, and of course it doesn't work. If they'd done that to your automobile, you go down to BMW and say, I've just ordered a car. Ah, there it is. Yeah, there it is. You know, $56,000, except we've sort of saved you some money. So we've taken $6,000 out and you've got no seats in the car, but we've got you, an orange box to sit on and drive down the road. And when you can afford the other $6,000, come back and we put the seats in for you. It is the most ridiculous thing in the world. Now, if you want to talk quality, and when you go there, if you go out there in the big world and you meet an architect and you meet a client that believes in you, that understands what you're trying to do, then you can go through with it. But when you look at it, it's a constant thing. And it has nothing to do with engineering. And it has nothing to do with mathematics. It just has just bad mathematics. Anybody can deduct a number from a big number.
Yeah. We say to our clients, it's not what you paid for, it's what you didn't pay for that's going to get you.
Oh, yeah.
Yeah. But see, we're down the daisy chain as mechanical engineers who support the architecture now. And when we do everything, and I'll come back to your thing about the big windows, because it's a good point you're making there, is we are virtually non-existent in the whole construction industry jigsaw, right? What happens is then we have this thing where America is very slow to pick up on. Building physics doesn't exist in the US. But building physics, what I tell a lot of my clients is that I get buildings to work for architects. We go back to the big glass. When we look at this, and you look at any glass, ASHRAE 90.1 says the code is 40% glass. Well, you show me a building in any city that's got 40% glass in it, right? So there again, straight away, you go from floor to under ceiling glass, you're up to 65, 70% of the facade. Now, there's a handicap which we have to overcome. So I'm going to put a question back to you, Robert. Who overcomes that handicap? Who works out and gets that building working for that architect with 65% glass in instead of 40% glass? And who is he?
It's you, Peter.
No, it's not me. Well, it's me and the rest, but it's a mechanical engineer.
Yeah, that's what I mean.
There's no thank you that what's going to happen. And what you've then done is you've enabled that architect to provide, let's face it, a non-prescriptive code building, but you've made it work because you can do it on a performance-wise. So they should be very grateful to our society, engineers, ASHRAE engineers, that actually make it work for these people.
Yeah.
And the challenge is not just to turn around and say, you can't do it, because I can give you a whole list of consulting engineers throughout the world that just say, here's the code, this is what you need to do. That doesn't solve,
Yeah. I was in Vancouver last week, Peter, and I thought of you because I took a photograph of the shoreline, and all of those glass high-rises had all of their blinds closed. And what came to my mind is that you actually had been doing a number of museums. And I remember listening to some of your lectures about, having to deal with artwork and artifacts and how the indoor environment was very critical. And one of the key things about those museums is you never see that artwork ever exposed to ultraviolet light. And you don't see it exposed to high levels of heat. You have tempered climates, moderate humidity. But yet every one of those easy bake ovens in downtown Vancouver, all that artwork in all of those buildings is getting destroyed by those glass structures, all that sunlight coming in. And I just think it's bizarre that we allow people to build buildings like that. And if you think about it from an energy perspective, like even with a 0.5 solar heat gain coefficient, 800 watts per meter squared, the balance of that energy coming into the building is equivalent to a snow and ice melting system. And we would never allow that to happen in society, to have every street, pavement, sidewalk melted. We just simply wouldn't tolerate, but we'd tolerate these glass buildings.
Because it's not seen, right? There's an iceberg effect here, right? You just see the top coming out. Below, people aren't aware of what's going on below the surface, right? There's the seen and there's the unseen. What's interesting on what you said earlier, Peter, is, you were working in Holland in the late 70s, early 80s on radiant solutions in hospitals. So that's radiant solutions at a commercial big building scale, right? So it's doable, right? The Romans were doing it. You were doing it. I don't understand the resistance in North America to radiant systems. I really don't. All I can come up with is supply chain and path dependency issues.
The resistance is, I'll have to choose my words very careful here. The main leaders to the resistance is, I think it was one of the American presidents, probably one of the best one, JF Kennedy, which we turned around and said that people don't like change.
Correct.
And that's one of the main things. People do not like change. The other thing that comes into it, really, to be honest, and Robert, we can write a whole book on this, is the number of people that have tried to do a radiant system and failed miserably because they haven't really understood how it works as operation, and also they want to cut corners, they want to save money. Now, one of the major things, we had a big debate at ASHRAE meeting in Seattle about active beams and VAV. The point people have to remember is the way the construction is done. It is not you shall, it's not mandatory. You shall use a radiant ceiling or a radiant floor or active beams. It's no, you can do it. It's up to the engineer of record who signs and stamps the drawings, who takes the liability. And there's your big answer why people do it. If you look and you go around, a lot of people think they understand a conventional overhead VAV system, and that's what they can do, and it's been going for years, and they talk to their friends and whatever, and the buildings haven't, and they haven't been sued. And along comes someone with a funny accent turning around, okay, we're going to run the cooling water through the ceiling or through the floors or whatever it is. It's panic and mayhem because people do not like change. And so to keep their liability down, they go back to an old way of doing things and just turn around and say, well, we go overhead VAV because the least number of people have been sued for that system.
And also the economy of scales there with this supply chain, right? I mean, there's thousands of VAV box manufacturers. They're there. Yeah. It's available. It's like going down Home Depot. They're on the shelf, right? So you can just take them and put them in.
We've had a very interesting thing here that's coming out from CBE in Berkeley. They're doing a $3 million research for the California Energy Commission on radiant floors in office buildings. And having done this for 35 odd years, one of the worst applications for a floor is an office building, because you can't do solar absorption because you've got office furniture and you've got people in there. And also, when you look at it, of how many BTU or how many watts per square meter you get from the floor, it's the least amount for cooling. So its overall efficiency is down for day one. So why would you do it?
Active beams is the best for office, right?
Well, active beams or radiant, or when it depends. It depends again on the flexibility. The architects and developers have got this great thing called churn rate. How often you're going to change the office. I say very brutally to these guys, candidly, let's not design for what is the future, because we don't know what the future is going to be. Let's just design it now for put a design partitions are going to be, show me it's going to be, and we design it. And when you come up with another design that you want to do it, then we work out what the costs are going to be. Because you cannot design to something which is an unknown. How's the office layout going to be in 10 years? And then you walk around these offices, and most of them haven't changed for 15 or 20 years. Some change every month, but that's the minority. The majority of this, when you look at what people are going to do, or, again, if you're going to change the office and do it, if it depends if it's lease or if it's an owner occupied. Owner occupied, then you can do the radiant, but you can do an underfloor, which is going to be better for that. Or again, what that engineer needs to do for that building, and that's the type of thing. Yeah.
That's interesting. So what fascinated me about your background is the fact that you've done radiant at great scale. I mean, you've done radiant on airport scale, which is pretty much as big as it gets for sort of commercial building use. There's multiple people from the public going through it. So can you give us some background on that?
Yeah. Well, it stems actually from thermal comfort, from Ole Fanger, from the where we get to it. The fact is that the big unknown in any building, which is always there, is the mean radiant temperature within a space. The biggest radiant flux within a space is the flux from a window. Robert was talking about in Vancouver, you can walk around there. And that's great if the sun's there, especially during the winter, you've got this low-hanging sun there, the glazing's in the sun for a long time. It might be minus 12 Celsius outside or whatever it is, but you still got solar radiation. What is the inside surface temperature of that glass? And the analogy I always use is because a lot of people get lost and get confused when they get in buildings, especially architects. They don't really know what they look like from the inside. But if you imagine that you're in your automobile, you're in your car, and you park it, and you forget to put the windshield protector up, and you get in that car at the end of the day, and you're driving down there, and you crank the air conditioning down to 66 degrees, and yet you still feel very uncomfortable because you start sweating, your head can't get rid of the heat, the cold air going over your body, and it's the fact that the windshield is at a temperature of probably 80, 85 degrees, and that's hitting your head, and you can't do it. And that's the simplest explanation for mean radiant temperature for when it goes, and it's negative. So then what happens is if you take you have the same scenario in a building where you can get the inside surface temperature of the glass very easy up to 80 degrees. People in an office, whether it's a single office or an open office, they cannot miss it because you've got this thing called the angle factors, the form factors, because there's a relationship from where the glass is to where the people are going to be. And the radiant factor comes in, okay, when we start looking at it, yeah, you can make a VAV run comfortable with that high radiant. All you do then, to compensate, you have to push the dry bulb temperature down in that space to, if you're in Celsius, we put it down to 21 degrees or 20 degrees, so about 70 degrees Fahrenheit. But obviously there's a big energy penalty for that. So the radiant comes in as well. When you do the math on it and you analyze what's happening, I've got this radiant temperature. If I put a radiant surface in there to compensate for that, I can balance it out. Then I don't need to drive the air temperature down, and I can look at the comfort of the whole year. I mean, it's a very simple mathematical process.
So would that could you describe that as a comfort-driven design process?
Yes, yeah, because we go back to those poor creatures called architects again that we love and other people is when we build these buildings, and when like Robert was describing, when you go down in Vancouver or walk to any city in the world and walk through there. There are people in the buildings. Those buildings have a function. They're not put there for architects' egos. The buildings are put there and you have a number of people in there. So if you actually look at the energy cost, which across the US is probably about $1.50 per square foot or something like that, right? When you're looking at it, yes, we do need to save energy and we go to net zero. What about the number of people that are in a building? What happens when you have 5,000, 7,000 people in a building, which is, 1.5 million square foot, 2 million square feet? What about that? There was all these years ago about the sick building syndrome, which came from the Netherlands over. People don't talk about it. But if you can go to a client and say, we can cut down, or we can, by improving the thermal comfort, we can reduce the number of sick days that your employees take. How much money is that? Has anybody ever calculated it? Because it goes into the millions per year. It goes into a big number.
Isn't it something, I heard the ratio, 100-to-1 ratio. In other words, for every $1 that goes towards building the building, there's $100 cost associated with salaries, workman's compensation, sick leave, all of that type of stuff.
Yeah. I mean, the simple math you can do. So if you take, a 1 million square foot building and then just to roughly say one person with 200 square feet, what's that, 5,000 people? Yeah. And if they're white collar workers as opposed to blue collar workers, then take a simple number, which is say $100,000 a year. then you multiply that by 1.7, which is all the overhead, which is the boss has got to do. So you got 5,000 people times, 170,000, right? Which is a long, big number, isn't it? And that's what they pay every year. Now, you just imagine that you could reduce that or have payback on that by even 2 to 3%, nothing more than that, 2 to 3%. That's a massive number, And again, it goes to show responsibility. Do you really care about the environment in which your employees work and in which everybody works? This is the thing. We've all heard about the downdraft. We've all heard about the air dumping and about the noise. I mean, we can write books and books and books on badly engineered buildings. But how anybody comes up and quantifies it and says, what is a good engineered building? And it doesn't cost that much more. It doesn't cost anything more. It just, it's a team effort to get it done. An understanding and a willingness from the owner, the developers, and the architects to get it done.
Yeah, there's an educational element missing, but also the incentives are really misaligned, because if you're a contractor and a building designer and a contractor building a building, quite frankly, you're so disconnected from the users of the building, it's just not your issue, right? Once your warranty period's done, you're out, right? No consequences.
Well, it does happen. You'll see some of the most successful buildings are the ones that are client-driven, client-owned, yes. For the major banks, you do that. Yeah. But you hit on another point, another one of my items which I wish would disappear overnight. One of the worst things that come, and I'm going to use a swear word now, that swear word being lead that comes out of it, and everybody's on a lead. One of the worst things it's done, and nobody's sat down and really looked at it, is when lead turned around and said that the design engineers could not commission the building, right?
Yeah.
And this is very interesting, because I think the people that cost the most, this is a contentious point now, the people that cost the most money in the modern day construction industry are the commissioning engineers, right? You don't know how many times I've had it in here, a bunch of guys that they're rolling off the streets, nice suits on, and then turn around while you're sat there and turn around to the client and says, oh, now we're going to get this building to work for you. You know what it is? It's like, go forth and get on your bike and go away, because when we started with this building, we had a blank piece of paper.
Yeah.
We started with a blank piece of paper. We divert this building all the way up. We know what the CFMs are. We know what the GPM in the pipes are. We know what the valves are there and everything like that. Why is it then I get these bunch of idiots in a suit, which are obviously failed engineers, because if they had any intelligence, they wouldn't be mission engineers. They would be in the first place, right? They would get on and do it. And to get these people in there. And then, when you look at what they're being paid to turn around and do this, and then the first report turns around, okay, this is our initial report on the building specifications. They were insufficient in this. And then you go back to the other one about the value engineering. Well, yeah, don't look at me. Look at the guy that took all the value engineering out of the building, right?
And that guy's long gone, right?
Yeah, what it should be, and no one's worked it out in good old America with all their business and things. If you do it the way they've done it over in Europe, which is basically they would withhold 10% of the contractor's last payment, 10%. Yeah. 5% would be the guarantee. The other 5% would be the fact of the matter is it would be paid when the consulting engineer accepted all the test and balance reports carried out by the contractor as to how the building should be delivered to the client. Right?
I'm with you. I think one of the big things in North America is Canada and the US. The Lean Act is a big reason for this. The Lean Act makes it very difficult for clients to hold money back, and it puts a lot of power into the contractor's hand. I've seen buildings go over that just should not have gone over because, there's a calculation that can be done and the money has to go, and it's terrible. I mean, and also to commissioning, the reason there is a commissioning industry, says the man who sold a commissioning firm, is the commissioning industry is an emergent property, in my opinion, of a design and construction industry that can't produce a building that works. Now, there's reasons for that below the surface, as you said, like value engineering, bad decisions, but whatever way you cut it, that commissioning industry does not exist in the car business, right? Because the owner, the manufacturer, owns the product.
Yeah.
Right?
Yeah.
The only reason there's a commissioning industry is because, for whatever reason, things are not being stitched together. This is why I'm personally a bit of the anti-VAV guy. I'm a big fan of simplicity and radiant systems and displacement. Yeah. The problem with VAV is there's no owner, right? There's multiple components, multiple people with their fingers in the pie. No one really owns it. They're complex. They're hard to set up and design. And then the FM team come in and fiddle with it. It's just a lose-lose. But the old energy model works, right?
Well, your VAV always works because it's so flexible and so over-dimensioned that at some point in time, when the control's there, it's always going to be good. I mean, it's a very good point because, I always use it very facetiously in terms and say as well, a typical VAV is going to be one box for 6 offices. And then you get people looking at you starry-eyed. And then it's like, well, the person who's got the thermostat's going pretty good. Yeah, no, people do it. And I said, well, you go walk down the office where you got the VAV, go around any building, any country in the world, any city, and you look for the VAV. And you look for the number of offices which are unoccupied but have got the thermostat sitting in them.
Yeah.
Right? And this is something that they need to do. And this is one of the biggest things going back to Radiant. The reason why Radiant is a lot successful and with the energy savings that it provides is because it provides individual control. Now, what the energy people need to look at is with the control is it's not like the simulation model and all these simulation jockeys. No, we don't always have 5,000 people in our office. It could be 4,800. It could be 2,000, 3,000, whatever the number's going to be. And then when you've got all these individual controls, it shuts everything down. But not when it goes back to the VAV. It's a turkey shoot. Yeah, if you've got the thermostat and the guy isn't in there, it's going to shut it down for everybody else. So then they're going to start doing things like with, putting, wet handkerchiefs over them to try and cook the thermostat and do everything else, And that's where it's wrong. But it's just a mind complex. Like you say, the Lean Act is a bad one. But if the client really wants his building to run in performance, then surely the client also has a responsibility to make sure that the building is operated as designed on the sequence of operation.
Right.
The main thing about being a consulting engineer is basically all we sell is, and Robert knows I have another reason for this, but yeah, is the fact that we sell time and hours. We sell 35 years of experience. To your original question, a lot of people still sell 35 years of, well, I've done it this way and I haven't been sued for 35 years, so is your overhead B&B with rooftop?
So there you heard it, listeners. That is the truth. Stay woke.
That is
But is one other analogy now, I just remember the analogy now, and this is a great one when you do a lecture. So what you do is you turn around to everybody. If you've got a good group of people there, you say, okay, so how many people have got a BMW? Go on, put your hands up. Put their hands up. How many people have got a Lexus? Put a Lexus. How many people have got a Mercedes? And that is. So you go through there and say, well, okay, we can assess that a vast number of the audience listening here have got quality cars. You buy that because it's a good car and it's your money and you do everything, yeah? So, yeah. Well, the next time the car wants a service, you should drive it down to the local fire station, park it on the forecourt, throw the keys in there and yell at the guys, change the oil, have a look at the tires and have a look at everything like that. By this time, like you're looking at me like I'm completely mad. It's exactly the same thing when you build a building of $200 million. Why do you give the keys to the janitor? Right? Think about it. The guy is doing nothing else but graffiti and stop blocking toilets, and he's got a $250 million building to run. Just think about how logic that is.
Well, this is my problem, right? Whenever I go to and have a look at an existing building, the first thing I do is go to the BMS and see how many of the control set points or systems are in operator mode or in hand mode, right? Because that's the default fix, right?
Well, the other scary story is, which is the new one which is the new Freedom Tower in New York.
Yep.
I went to a lecture and the lecture was there and it was all about architecture. And then one of the guys said, well, what about mechanical systems? And the guy turns around and he was very happy to tell about the mechanical system. He said, yeah, it's floor by floor DX. This is 2 years ago, 3 years ago, right? Now, there is a reason for it. It makes no sense, but there is a reason for it. Now, this is how the world goes. So what happens is with the New York union law, it works out. If you have a pumping system, you have to, like it used to be with absorption chillers, you have to have 2 or 3 people. Yeah. But how can a building like that that's supposed to be LEED platinum get all that different stuff, knowing that from a systems perspective, a systems efficiency perspective, it's probably the least effective you can have. But to save how much a year on employees' cost, are they willing to go and put that system in there?
That's outrageous. I never knew that.
There's even a better one if we want to talk about One Bryant Park. with its EUI. They had this, I call it a green beanie tree hugger, guy come in there to do everything, to do a review for a magazine. And he's walking around and looking at the building. We're going to do this and do everything like that. So he finds out, he says, what is the EUI, the energy use index? And it comes out, it's 327 kBG per square foot. And people are looking at this and going, well, is it bad? Well, in New York and 17 other cities in the US now, they have every building operator has to provide their utility usage at the end of the year so you can work out what the EUI is. This building is 3 times as much as what it should be, right? This is the site energy, not source, the site.
Yeah.
And they're blaming it on, it's because we got trade. You don't have traders floors on every other floor on a building like that. You might have 3 full traders floor. And someone else started arguing me. He said, there are 18 floors of traders floor. It's going to be like a nuclear power plant. It's not going to do it. Yeah. It still doesn't matter. The fact is that people build this, and that also is a LEED Platinum building, right? And, where do we get to? It's obvious that someone's cooking the books. It has to be. Because one of the things you've got to put in on your lead form is what the EUI of it is. You go to Energy Star, you go to Energy Star and pick it up. And you put down there, if you put 327 down there for what the EUI is going to be for the building, well, it's obviously somebody left something out. Well, what else did they leave out? Right? It's a scam. It's a con.
The Edifice Complex will continue in just a moment. If you're enjoying this podcast, we need your help. We're not asking for money, just a minute of your time. Our goal is to make the Edifice Complex podcast as relevant, educational, and useful as possible. By having good ratings, we can reach the widest audience. Therefore, our request is 2 small things. If you haven't already, leave us a review and rating on iTunes. And subscribe to the Edifice Complex on YouTube, even if you normally only listen to the audio version. These 2 things will help us immensely. Also, if you would like Robert or Adam to speak, teach, or consult on your project or business, please email admin@edificecomplexpodcast.com. Thanks for your time, and now back to the show.
So you designed the radiant systems for the Bangkok International Airport. So just so that people understand what a difficult task that is, we're talking about an international airport with thousands of people going through every day, a massive building of glass, no doubt, and concrete, and it's in a tropical climate. That's about as difficult as it gets for designing radiant systems. So can you just take us through what happened there? Because that was a bold decision to do that. And did it work is my basic question there. Was the outcome great?
It seemed logical when you look at it from what happened. I mean, you mentioned about a lot of glass. It was a lot of glass, but the rest of it was ETFE in between as well. There's all stories about that because they tend to have airplanes at airports, and when you look at the noise level going through, the glass and the ETFE doesn't give that much sound attenuation. The other thing that we did when we were looking at it was also we did rely on CFD, computers for, computational fluid dynamics. Yeah. Or as we call them, colors for directors, because it's just we had it numerically. So what was the stratification process, and that was mainly from the radiant floor and from the displacement, because people only walk on the first 2 meters or 6 feet or 8 feet of a space.
Right.
So why was it? See, there's also a trend. Jet Black Cock had been built, which up to that time was like the biggest when it came there. And that had what they call the air fountain. So they use lots of air in there. So you put the air in there and you blow all the air around and you maintain 22, 24 degrees. But because it's fully mixed, you're still doing that under the roof. Now with Bangkok, we looked at it and we thought if we can get stratification so we can keep the first 6 feet, 2 meters, call it what you will, at about 21, 22 degrees. And I'll tell you what that was in a minute. But the rest of it could float up. So basically, the temperature on the inside of the skin to the outside of the skin was the same temperature, then you have no conduction, heat lost from the space. Whereas if you just look simply back to Jet Black Cock again, that temperature was 24 degrees and 34 degrees outside, then you had a constant 10-degree conduction loss over the whole skin area. So if you take it the same as the floor area, that again was 5 million square feet, which is a big number.
Yeah.
So we let that number float up. And what we could also do was a controllability, because you could turn the air on and the air off. The actual design that we used was a comfort design. And even then, we were looking at 800-seater planes when we would just use 2 gates. But the critical thing was a 400-seater plane with all the staff and everybody that we've all made, is where the plane goes into a technical and is cancelled. So they keep you in the gate. So you've been in there probably for an hour, maybe an hour and a half before the plane leaves. You're not getting on the plane because they know there's something wrong. Whichever way happens is, if you're nervous about going or you don't know what you're going to do or whatever's going to do, can you catch your next flight? Your metabolic rate increases. You can't take your clothes off and adapt your clothing. And so everybody's stuck there and frustrated. And that was the design conditions that we used for Bangkok Airport, for all of the gates. So the metabolic rate we had was nearly up to 2. It was insane. But if you want to go down there and fight your way through 400 people teed off when the plane isn't going to go, and that was a design condition because we wanted to maintain the comfort. So the radiant floor was there because where people were going to be walking all over the place, and it's a large open space. And the displacement, the thing we did do with Flack and Kurtz, we went up to Finland and we were testing both with Holton and with Trox to actually show them how displacement worked. They hadn't seen it. And I can remember we were in one of these big halls, and the only thing that stopped the air from moving anymore was it hit the back wall. They just could not believe it. Still got the original smoke test. So they understood that. The other thing about it for a maintenance purpose in the architect, it was because we were coming out the floor, all the distribution ductwork was underneath that floor. So there was no overhead pipe work. There was no, if you look at it on that airport, the efficiency, the number of mechanical rooms, they're sort of like 1/3 of what they would be in a typical airport. So again, we're looking at what we've got. We've cut down on all the duct work and the sheet metal work because it's much easier to pipe the water around there. We're looking at how the chillers can run. I mean, I think Bangkok was 28,000 tons or something like that. That's how much chilled water was running around there. So that was it. We did do solar absorption at the time in some of the areas with the glass. I mean, there was the 1 million square foot glass roof over the departures and things. So there was so much. And when we actually looked at I've got it somewhere what the actual prediction was. I think it was about somewhere between 30 and 40%. I can get more accurate. That was what it was compared to a conventional airport such as Chetlak design. So if it was an overhead VAV, what it would be. And that was just in the pure energy without looking at, like, say, sheet metal, looking at maintenance, looking at everything.
So how did you deal with humidity issues?
Well, okay, that's always a good question, that is, because humidity comes from the 400 people to 600 people. See, once you've done museums, it's exactly the same. The museum doesn't work on temperature, but works on humidity. So you have then 50% RH plus or minus 2% or 1% in some of these big ones, but you still have people there. So let's talk about an art gallery. So when you have a 5,000 square foot gallery of 500 square meters, you have 500 people come there for a reception. You can't turn them off. That's the biggest latent source ever. So once you can do that, so basically all your air does, your air takes care of the latent heat or the removal of the latent gain within space and balances it out, and your radiant floor works on it. And that was exactly the same thing as we had in the airport. To go back to the airport, the only thing we did do was Murphy's Law did come into it, and that was that the first 5 meters from the door, we didn't put any radiant loops down there just because it was there. And if you go to the airport, unfortunately, what happens is, or fortunately, what they do is the porters always keep the handicapped doors open. And these are pretty massive doors because they don't want to bother it when they're moving the bags through. So, and I've been in there, and there's no humidity, no nothing. There's no water on the floor whatsoever.
So, if you were doing that area again, would you put a big vestibule in to deal with that?
Well, the vestibule comes when you do that. You also have them with fire and life safety. Yeah. Which way does the vestibule work and where you're going to do? Yeah. Yes, it would be in that. Well, what would be common sense would be to leave that big door closed. I mean, that's why we have the doors.
It's a design intent, right?
Yeah, but if you go back and look at it again, that there was no condensation, there was no water around there or anything like that, then one could turn around and say, well, we don't need it. We don't need the vestibule. We just need where we are.
Did you do anything special with the facade? Was it a special, like, super high quality facade, or?
Yes, the facade. This is a good German story. This is. So, anybody? So the glass and Transolar were working, and Transolar came up with this glass because it had to be a monolithic glass because it was being bent. So it was 2 layers of glass, and there was a PVB layer. So what they worked out is that one side of the glass would be white frit, and the other side of the glass would be black frit. And it got to the point when they actually turned around and said, but the way the glass manufacturer had to manufacture it is that both frit, so this is a fritted dot, a 5 millimeter dot, that both of the dots on both of the pieces of glass had to match each other exactly.
Oh.
That conversation lasted about an hour, and it was like, no way is that going to happen. But if you look at it, but then also the frits were on the higher levels, it's 70% frit, and it all came down to the first 2 meters, and then it was 0% frit for the the view factor. And if you're in there, again, we got photographs of it because the eye, you look to a higher intensity, so you look through it, you don't see the frit.
Right.
Outside, you look to a lower intensity,
right,
then you see the frit. But if you look for the daylight harvesting, I mean, if you go through that airport, there's hardly any lights on, only at nighttime and everything, there's hardly any lights. I mean, it has its war stories where they introduced a secondary security, right, and they put them, there was a connection from the main terminal building to the concourse, and there were these 2 ramps. And it was ideal to put a secondary security in there, and unfortunately, the people that suffer are the people that the security guards, because they're in that for 8 hours a day, and then that's where you'll see lots of these makeup units and portable air conditioners, and then everybody says, "Oh, the airport doesn't run." They forget the other 5 million square feet, But
that's the thing, right? When you do something that's unusual, it draws out the trolls and haters, but. So what I hear is there are benefits to this project, right? One is the net to gross is way better, right? The net to gross area, far less mechanical rooms, less capital cost, less ductwork, right? And less energy use. Do you know what the EUI is for that building, the actual?
No, not going to guess. I need to look at the numbers. It was compared to what it was. And then the other thing, see, obviously with the EUI was being in Asia, the flights would either leave late at night or early in the morning, and then during the day it's domestic.
Right.
I mean, it was designed for 60 million passengers a year. I mean, you go figure what that is,
Yeah, that's a lot. How many square feet was it? 1.5 million square foot building? Something like that?
No, 5.5. 550,000 square meters, yeah.
Bloody hell.
yeah. It was 70 odd gates, and I've heard that there was always plans to build like a satellite concourse, and I believe they're going ahead. The main thing was that they had with Thailand was that they hadn't enough money, or it was Japanese money to purchase it, but they didn't have enough money to pay for the electricity for the people mover to get people in and out, and that was also the problem to get from one concourse to the other. But the last story I heard, I think it was about 6 weeks ago. 4 weeks ago, I was in Hong Kong, and one of the guys was telling me that they're going to rebuild it, they're going to do it, but it's going to be a conventional system just because of the people that they got working on it, So it will be interesting. It's a pity, but it's the way life goes.
It's a great project example. I mean, I hope some people are writing up about what's happening post occupancy, because that's where, for me, that's the interesting thing, right? Does the client believe it's successful? Are the energy savings real? Are people happy with it? They must be. I can't see how they can't be.
Because it's run as a business, the Airports Authority of Thailand that run it, none of this information is free coming. The other thing about it is, in their defense, they have nothing to compare it to. It's their only airport, and when you start looking around the world, I mean, there are some reports or some comparison, if you take Changi in Singapore and Hong Kong, and then look at the big ones that are going, the ones that were built, Beijing, which was built very hastily for the Olympics and other different things, There's all these airports coming, and I think that quite possibly, as I've sort of lost track, but I guess that somewhere along the line there might be some energy comparison of what they're doing.
So just to talk generally then, are you the go-to guy for Radiant? I mean, do people, if someone's like sitting in their office chair, corner suite thinking, I need a new airport, I think I'll have Radiant. Is there a buzzer on their desk to call you?
No, actually, if I hear of something like that, I'll be on the plane straight away, banging at their doors, No, I would like to say, I mean, there's an old saying, isn't there? You can't put an old head on a young person's neck, so there's all the years of experience of doing things. Right. And, Robert can tell you, we're going to be doing this thing for ASHRAE and everything like that. 90% of what we're saying is common sense, and you look at it and you do this, people. I mean, I can name other people that are trying to design radiant, and it's like, why not do this? And then the biggest problem always is back to the value engineering again. People that want to try and skimp on it, and it goes out there to the contract, and it goes there. I mean, I had a good friend of ours, I won't mention his name, but he called me up and he said, yeah, we've designed everything and the contractor's taken everything out. And I said, you better write a letter to the client and to turn around and say, look, you sold this as a sequence of operation with all this equipment in it. If that equipment isn't installed and isn't delivered and isn't operated and anything, then you are totally not responsible. You've got to do that. And unfortunately, because it's, like I say, it goes back to America being the cheapest. What I don't understand is dealing with people is why people feel the need to remove costs from a building and from a system. And it's nearly always controls. They don't understand it. It shows a total lack of understanding and a total lack of respect for the construction industry and for engineers that design it for a purpose.
Engineers need to grow a backbone and do more of that, like write the letter when the contractor comes in and starts cutting the jobs. If that happened more often, it would give clients pause when they come to the value engineering, right?
Yeah. Bring this down to a scale that some of our audience, are building smaller buildings, not larger buildings.
Yeah.
Let's take, for example, someone that's going to buy a Ferrari or a Piper plane or some kind of a yacht. That individual is going to spend, several hundreds of thousands of dollars or $1 million on that transportation. Let's say they spent, $500,000 on elective surgery. You can bet your bottom dollar that they would do the research work. They'd find out who the doctor is, what his reputation is. They would do everything they could to find out about the car manufacturer, the boat manufacturer, the plane. But why is it they'll spend $1 million or $250,000 on a mechanical systems and they won't do the research work? They put their faith in a building industry that doesn't know what it's doing, and they leave it up to them. And that's one of the problems that we have is we have buyers that won't do the research work.
It's a great point what you're saying. I mean, we can go between the two, between residential, which I know you're involved in and been involved in some residential myself, is when you look at it, well, residential is you need to sit down with the owners before the house is constructed and go on and ask them what do they want, And I've had recently here in California, with La La Land, and this several houses were sold by a certain developer that were going to have a radiant system in, and it was 30% more efficient than a normal system. That's what they used. It was in there. Now, one of the families we're dealing with, I spoke to them, they came from New York and sat down, and they didn't like it, and they'd actually tried to crank the thermostats down to make it, and they actually made the floor sweat because they put lower temperature water through there, and they were not happy, right? Now, did they bother to look at their specifications when they bought the house, when they signed on the dotted line? Did they really? They wouldn't know it. But now, then it's like a blackmail system because all the pipes are buried. Yeah, they got the one thermostat on the wall running with their video system or what else it's going to be, and they're not happy. And I said to them, I said, really, you want to do the same as New York, where you've got an all-air system. You can come in from your car, you can bring your shopping in, bring the kids in from school, walk in there, flick the switch, and within 15 minutes, you've got air buzzing around it. Exactly. Well, then you don't need a radiant system. But it's the interpretation. Now, you get other people that are going to be in there on a day-to-day basis that are there with lots of glass and sit around and do everything, and then you've got the radiant system with the compensation again. It's ideal. It's fantastic. But what you're trying to say is it's the understanding, but also, Robert, you've got to look around. Who explains this to them? Okay? Would you buy a building from an architect, a big building from an architect, if the architect just explained to you what was going on? He'd tell you about the finishes in the toilets and how the stairs were and everything. Right? You think an architect can tell you now about the rainwater drainage system or the sewage system from their building?
Yeah, the things that matter. The things that cost money long-term over the operation of that building, right? They can't tell you that.
It goes back to what I said about the janitor, the facilities managers, what they do. They're the people that are left holding the baby at the end of the day.
Yeah.
I think the answer for residential is some firm will come along and vertically integrate everything, design, construction. I don't mean traditional design and build. Someone who's going to own that widget and be accountable for it post-sale. The iPhone of houses is what we're after here. But at the moment, what you got is the Windows and the Dell thing going on, right? Where it doesn't quite gel. I don't know. We're coming up to an hour here. This has been awesome. And I know you've recently been published, done a ASHRAE publication on tall buildings, right? I'd love to get you back in the future to talk about that if you would. But in the meantime, what I'd like to do is wrap this up now. If you could let us know your contacts on social media or any websites you've got, and we can put that in the show notes and people can follow your work. What are your contacts? Are you on Twitter?
No, I don't do Twitter. I don't do LinkedIn. I don't do anything like that. I do believe in the telephone number. The easiest thing is my website is up and running, and that is very simple. www.petersimmonds, all lowercase. Simmonds is SIMMONDS.com. It's got all the information on there, how to get in contact with me, and it gives a description of what work I like doing and some photos of some of the projects that I've been lucky enough to work on.
Awesome. That's great. Well, I'll make sure that's in the I'll start again. In the show notes, excuse me. Listen, thank you for coming on. That was awesome. I'm a big fan of Radiant, and I cannot wait to fly through Bangkok and check that airport out.
Okay. Thanks, Peter.
Thanks, you guys.
So, what did you make of Peter then? That was a good interview in my mind.
Adam, I've known Peter a long time, many decades, and I always look forward to talking to him. You know, we've talked about a lot of stuff over 20 some odd years, 20, 25 years, and I always learn something new. He's always got something on the go. He always has an opinion.
Yeah, I like that about him.
And, you know, as far as a voice goes in the world of and not just the world of architecture, but the global world of architecture, because he has been everywhere learning and sharing his knowledge with these projects. And the Bangkok airport was really cool. We didn't get a chance to talk to him about the project he's working on in Korea, unfortunately, not a whole lot. He mentioned it a couple of times, but it's bigger than Bangkok.
Also, different climate, right? He's dealing with hot and humid and cold and damp. With Radiant, interesting. That's even harder in a way.
Yeah, exactly. Yeah,
but he's doing it. I like the fact that he's doing it. And I like the fact that, I mean, I've not been through Bangkok in a long time. It's going to be interesting next time I go through. It'd be like doing a deficiency list as I walk through the building, right? Yeah. You're never off duty, right?
Yeah, exactly. So what did you learn?
What I really liked was the way he was using thermal comfort as a driver of the design process. It wasn't energy driven. There was a thermal comfort factor to it. In fact, when I said that, he sort of agreed with me. It was one of the driving sort of design principles, right? Because in that climate, thermal comfort has to be a driver, right? Otherwise, it's just going to be hot and humid. It was really interesting. And I like what he told us about the facade, using the frit and then just making sure the view window was there, but using the frit and then using stratification. So basically, he was designing for a 6 foot high level in the building with the view corridor, right, to the outside. The rest of it be damned.
Yeah, exactly. So that and the displacement ventilation and the radiant cooling, which you had said before, you know, mentioned it in a couple of other interviews that we have done, that combination.
Yeah.
You know, really, if you could create a recipe for high performance buildings, you know, it's good enclosure, well thought out window to wall ratios and fenestration systems. It's low VOC materials. It's displacement ventilation with a dedicated ventilation system and radiant.
Very interesting. Very interesting. The other thing I did like was when you were saying, you know, mechanical engineers enable architects. So all you mechanical engineers out there and building service engineers, that is never a truer word said, in my opinion. It's to say you're almost like a parachute, a safety net sometimes, right?
Well, you are. Well, you know, and even if we think back in our own careers, how many times we've had to go in and solve problems that manifested themselves as a comfort problem or an air quality problem or a sound problem. And it was always, you know, the finger always came back to us as the engineers, the designers and the technicians. But ultimately, in those cases, it was an architectural problem or a building enclosure problem.
Yeah, I also liked his statement, you know, Now, everyone listening to this should know, despite Peter's English accent, he is actually an American as well. And he said, America's the cheapest place to build, basically due to the shitty value engineering. Lead is bullshit, and building physics does not exist in the USA. Those are pretty bold statements. That should trigger a few people.
It sure should. Well, and it sure should. I guess I should change the inflection, because if you're paying attention and you're listening to these people that we're talking to, guys like Simmonds, these are world-class individuals, and there's not too much they haven't seen. And when they stand up and make a bold statement like that, pay attention.
Yeah, I mean, to bring this to pop culture level, for me, he's one of these guys. He's experienced, he's senior, he's been there, done it, and he's sort of like when a job gets in trouble, the bat signal goes up, we need the radiant expert, and it's him, right?
Yeah, absolutely. Yeah, absolutely.
He's the mechanical equivalent of Batman, maybe. I don't know. But and Peter will admit this, is that, in his own world, he can't exist without a great support team. Yes. Yeah.
And because without that support team, he would get bogged down in details that just really don't interest a guy like Peter.
No. He should not be a detail guy. He's the guy that should be solving the facade, frit level equation with the thermal comfort equations. He shouldn't be detailing any drawings, man. What a misallocation of resources that would be.
Yeah, well, and then I got to think that happens a lot in engineering firms, a misallocation of resources where they have guys that need to be set free, to do the stuff that they're really good at, but they get caught up in the day-to-day managing projects, and which is unfortunate.
It is. I mean, this is where the skill shortage in engineering design firms manifests itself, right? So you have a guy like Peter, he should be doing concept and the heavy engineering. And then there's a senior, an intermediate, and a junior below him who are doing the other stuff that's appropriate to them. But because of the skill shortage and the lack of people coming out of university, that middle is missing. And sometimes I've been in firms where people like Peter are bogged down doing toilet extract systems. It's just ridiculous. Waste of talent and time.
It is a total waste of talent, especially when you handcuff them with all of the administrative stuff that we throw at these people, and talk about a way to frustrate a good engineering mind, right?
Yeah, I mean, you can see why sometimes on big firms where there's understaffing, senior guys leave just because they wind up doing stuff they shouldn't be doing, right?
Yeah,
it's a that's a mismanagement of resources, right? I guess is one way to look at that.
Well, one of these episodes we'll talk about, I think we should have an episode on business, and because you and I have both bought, sold, operated businesses, and the horror stories that we have with, signing a company over to somebody else, in exchange for cash, which is a nice way of getting compensated. Can't be angry with that. But, they do such stupid things afterwards. And, I think we should have an episode on that.
Yeah, we should have an episode on business. We should just wrap this conversation up with, my master's degree is in project management. And one of the early lectures I went to was about misallocation of resources. And the opening statement went like this: the pass mark for this course is 50%. This is the UK, guys. It's different in the UK. 50% is a genius level mark. And a distinction is 85, and there's nothing in between. So if you get more than 50%, you have misallocated the resources necessary to pass this course. That was essay number 1. Now,
my fans here thought that was pretty funny.
Yeah, I think it was a reverse engineering brain, where he was trying to get us to do more. I don't know. I came out of that lecture very confused about what the message was. Should I be trying harder? Should I be trying less? It was really interesting. But he was right. You should do what's necessary, but not more. That's the argument for not over-engineering, right?
Yeah, and that wasn't it Freud or Einstein said something like that?
Yeah. I don't know. God, if Freud or Einstein was an engineer, that would have been interesting.
Something along those lines. You should, do something, but not more than you need to do. I can't remember how it went, but I agree with that. And oftentimes, well, this too. I mean, as we do designs, and when you're when you're picky about designs, it's hard not to keep putting in that extra hour or 2 hours or 3 hours into the design. Even though if you release the drawings, they would be adequate enough for construction. There's a part of, I think, every good engineer that just says it's not good enough. And overcoming that is a hard thing.
This is the problem with our businesses. There's a lot of ambiguity, right? So when you work in the States with American teams, it's like, oh, we've done 40% drawings, we've done 80% drawings. 80% of what? So anyone who's listening to this, let's all agree, 80% drawings is bullshit, because 80% is what, right?
Yeah.
You know, when the architect says he's 80%, if you cast your eye over to the mechanical engineer, if that guy's more than 40%, I'd be astonished. Right?
Yeah. Yeah.
You know, there's so much BS. Somehow that's got to be clarified. There needs to be some objective measures for that. But again, part of the reason we're doing this podcast, right? We're trying to heap disrespect on people who desperately deserve it and highlight nonsense. And the statement 40% drawings complete, I'm telling you now, is complete and utter nonsense. There you go. That's my rant for the day. Done.
So what are you reading these days? What's on the reading list?
Oh, I've got so many things going on at the moment. Podcasting and reading. So reading, I picked up a book the other day. I haven't picked it up for a long time, by Robert Petitjean. He's a Belgian guy, right? Total Hydronic Balancing. He literally wrote the book. I saw that guy speak in London in the mid-90s when he was launching that book, and he came to a series of lectures. And he went to an ASHRAE conference in London, and there was a big debate between him about sizing control valves and should hydronic systems be balanced. And there was an American guy there who was on the I don't need to balance it side, and he was on the everything should be engineered side. And he demolished this guy. I mean, it was just embarrassing. And I was just flicking through that book the other day. It was such an awesome piece of work. Very academic, but you could still get out of it what you needed. I recommend that book to anyone. Total Hydronic Balancing by Robert Petitjean, who I think has passed away now. He was a professor in a university in Belgium, but he worked for TA Hydronics when he wrote that book.
Yeah, University of Charleroi.
Yeah, absolute genius.
Yeah.
Great presenter. Smoked like a chimney. When he wasn't up talking, he was chain smoking. He was brilliant, man.
Yeah. He's and it's one of those books that should be right beside your desk. And I've used it, for probably 20 years now. Always going back to it because I'm always learning on every job. And the more I learn, the more I understand what's in that book, and the more I can apply what's in the book on the next job.
Yeah. So again, just to wrap up with a controversial statement, and I have this fight in North America on most jobs. If you're a building services or mechanical engineer and you are designing a hydronic system, it is 100% your responsibility to size that control valve and check it for authority. It is not the supplier's job to do that.
Right.
Hopefully that's triggered a few people, and I'll be happy to have a debate online with anyone over that.
Bring it on.
Yeah,
absolutely. I'm with you.
I will put in the show notes some information on that book. So if anyone wants to link on it, I'll find it somewhere and put a link in. And you can see, so someone, if they wanted to look at that book or even buy it, they could get it somewhere. I'll research that. So what are you up to? Have you seen anything this week that's really triggered you? Like a snowflake?
No, but I am redoing my mechanical room. And, right. Yeah, well, it's like anything else. You have to maintain it. And, so for those that are, if you're a property developer or a homeowner or whatever, it's a mechanical system, and you just can't lock it away and think it's going to be good for the rest of its life. You take your car in for tune-up, so you got to get your mechanical room tuned up. So I do that once a year. I give it a good tune-up, and I have a great guy that I trust, and he keeps the room operating the way it's supposed to operate. So
in the UK, we have a saying, right? The worst car in the world is the mechanic's car. So this is an engineer's mechanical room. Is it good? Is it awesome?
It's great, man. It's one of the best. It's one of the, it's not one of the best, but it's close to the best. And, we have, here, I'll show you, because you got the camera, right? So that's Pete. He's my man.
Hey.
And,
how are you?
So we're going to put a picture of this mechanical room in the show notes. It better be awesome. Let's have a look.
These are some of the early prototype panels that we built for Danfoss. That's why they bought our business.
All right, interesting. So for people listening here, the mechanical room is chock full of control valves and pipework. It's quite compact. Now, I always remember when I first met Robert, he told me why he posed the question when he was instructing a course I attended. Why are mechanical rooms not like consumer goods and finished properly?
Yeah, absolutely.
So I can tell you, when you see the picture, Roberts is on the way to that.
Well, what it is, it's all the prototypes that we were building. And so the very first, model 0001 are in my mechanical room. And as we, of course, change out and fine tune the room, we'll replace those early prototypes. And but I'm a firm believer that mechanical systems should be consumer based, because ultimately it's a consumer that operates it or buys it. And I have some very strong philosophical differences between many contractors and suppliers about customized stuff on this job site. And we get into some great debates, and you can always tell when you're dealing with a contractor that owns a contracting business and a businessman that owns a contracting business. Those are two different operators. And the business guy operating a contracting business, he's interested in cash flow and profitability. Yeah. And for him, that's keep consistency. Let's run this like a machine, a factory. No custom stuff, no one-offs. We want to be able to go to the same job or the job that we did 20 years ago, and we want to know that what we did 20 years ago is the same stuff we're doing today. That way we only have to stock one set of parts. We know what's on the job that went out 20 years ago, and we know what's on the job that went out a week ago.
Yeah.
Stop the parasitic drain on our profitability by doing all this custom stuff. And that's what our whole philosophy was with the panels. That's, now, it's a philosophy we've been teaching for over 30 years. And that is that standardize. Yeah. It's like real estate, location. Mechanical systems is standardize.
I'm a big fan of modular construction. And maybe if we can find a modular construction expert, we should get him on the show. Because I'm a big fan of that. And there's a bit of a clash with that approach with the union issue in North America, but, it can be done, because in a factory you can control quality, right?
Yeah, absolutely.
And that's the issue. Yeah. All right, that's a good spot to leave things on. So, okay, I think we're done for now. So until the next time, arrivederci, everybody.
All right. Good talking with you again, Adam.
Okay, take care. See you on the next
time.
You've been listening to the Edifice Complex podcast with Adam Muggleton and Robert Bean. To access show notes for this episode, visit edificecomplexpodcast.com. Also, if you would like Robert or Adam to speak, teach, or consult on your project or business, please email admin@edificecomplexpodcast.com. See you next time.